As ready as I'll ever be. Yeah.
We're happy to have our frequent visitor, Rocco Servidio, here to tell us about property testing.
Thanks. Learning and testing. Yeah. Thanks, Ryan. So this is going to be a talk about learning and testing k-modal distributions. It's work that's in progress with Kostas and Ilias. Okay, so what the talk is going to be about at a high level is studying probability distributions over a very simple domain, 1 through n. And it's going to be important, we'll see, that we think of this as like an ordered domain, 1, 2, 3, 4, not like an arbitrary n element set. So one particular type of distribution we'll be thinking about are these monotone increasing distributions. And what I mean by this is just that the PDF is an increasing function, right? So the histogram looks kind of like this. We'll see a lot of pictures with this general flavor in the talk. Oh, and something I should mention, I guess, is that I'm going to be a little sloppy in my language. It's too painful to say non-decreasing all the time for increasing. So when I say increasing, I mean non-decreasing. And I'll say strictly increasing if I need that, but I don't think I'm going to need that. OK. So more specifically, the talk's about k-modal distributions. What's a k-modal distribution? Well, it's just one where you look at the histogram, and it's got like k peaks and valleys. This would be an example of a unimodal distribution. This would also be an example of a unimodal distribution. Does this thing have a laser? It has laser power?
Top button. It's green, but it's not too strong.
It is there in your.
Oh, wow, it's tiny. Yeah, yeah.
There's a physical, you can just stay right over there.
You can walk and point.
OK. I'll also walk over and just point to it, yeah. This is another unimodal distribution. It has one valley instead of one peak. Here's a 3-modal distribution. So we get the idea. OK, so what's the basic kind of learning question that we'll be thinking about? The basic learning question is we want to learn an unknown k-modal distribution. So the target distribution is not known to us. It's a distribution over these endpoints, but we're promised that it's k-modal. I worked on this for a while. Can you see like some very hazy, you can't see it. Can you guys see like ever so faintly like a histogram there?
A little bit
Too bright? Yeah. Oh, thanks. I'll just use the stick. I prefer the stick, in fact.
Actually, it even has a remote. So if you want to
Oh, wow. Yes.
Wow.
you can plug it in.
Oh, there we go. Wow, thanks. OK.
Anyways,
Yeah, so there was a hidden. No, that's perfect. That's fine. Yeah, yeah.
Sure.
So there was a hidden. Yeah, I'm good. I'm good, Dimitri. Thanks. So there was a hidden, k-modal distribution there, see? And the algorithm, is going to get samples from the distribution, so it just gets draws from the distribution. And we want to learn some high accuracy approximator of the unknown distribution. And for the whole talk, we'll be talking about variation distance, just the L1 distance between two distributions as our sort of accuracy criterion. OK? And of course, what we want is an algorithm that doesn't use too many samples, hopefully something like the information theoretic minimum number of samples, and a computationally efficient algorithm. So that's the basic learning problem. We're also going to talk about a testing problem. And we actually study a couple of different testing problems, but in this talk, I'll just deal with the simplest one. The particular testing problem I'll talk about today is that we have a known k-modal distribution. That's this distribution Q. So you have like the entire histogram for it. You know everything about it explicitly. There's an unknown k-modal distribution, P, and we get samples from P. And we want to figure out, is P the same as Q? Is it the case that P is equal to Q, or is P far from Q? If P is the same as Q, we should say yes. If P is far from Q, we should say no. Epsilon far from Q in variation distance. And if P is epsilon close to Q, all bets are off. We don't have to do anything in that case. So these are the problems we're going to think about. I should mention here, let me just spend 30 seconds and tell you the testing problem we're not going to solve, because this problem will actually come up later, but I don't want confusion about it in the beginning. So the testing problem that we're not dealing with is that you get samples from an unknown distribution P, and you want to figure out if P is k-modal or not. That's not what we're doing. That's a really hard testing problem. And there's like a simple lower bound that tells us that it's really hard, right? Suppose I promise you the unknown distribution is either uniform over an n-element set, or else there's a randomly chosen subset S, and it's uniform over that set. Well, this distribution is monotone and one-modal. It's like very simple. This distribution is far from any, I don't know, n over 4 modal distribution, right? But if this is a random subset S, and you just get something like square root of n draws from the distribution, you can't possibly tell whether they came from this guy or this guy, because in both cases you'll just get, you'll never see the same point twice. Okay? So this little example will come up again later, but it's not the testing problem we're dealing with. The testing problem is we have a known k-modal distribution, and we want to know, is the distribution that we have samples from that known k-modal distribution or far from it? Okay? OK, so why are we interested in these questions? Well, I don't know. These k-modal distributions seem like a pretty simple natural class of distributions you could think about. Maybe one way to decide whether these k-modal distributions are natural or not is to ask yourself, can we solve different kinds of algorithmic problems more efficiently for these distributions than we can for general distributions? So it would be nice if that structure was something that algorithms could do something with, and we'll see that is the case. And kind of a sneaky post hoc justification, as we'll see, these solutions we have for these testing and learning problems give us kind of interesting connections between testing and learning. Our learning algorithm uses ingredients from testing, our testing algorithm uses ingredients from learning, and so on. OK, so before we get into these specific questions, where we're interested in learning k-modal distributions and testing whether a k-modal distribution is equal to a known k-modal distribution, let's just think about the general versions of these problems for a sec, where we don't have this k-modal assumption. So in the general case, if we drop the k-modal assumption, the learning question is very simple. It's just you've got some arbitrary distribution over n points, and you want to learn it to variation distance epsilon. So this is very well studied. You need n over epsilon squared samples to solve this learning problem. That's kind of a lot of samples, but what are you going to do? There's no structure here in this distribution at all. So that's like a baseline. We'd certainly like to do better than this. For the testing question, if we're going to drop the k-modal assumption, then the testing problem is what? We have a known arbitrary distribution q over our endpoints. We have an unknown arbitrary distribution p over our endpoints. We get samples from p, and we want to know, is p equal to q, or is it far from q? And this is one of the first problems that was studied in the context of testing probability distributions. This work by, I guess, Fortnow, Rubenfeld, and various collaborators. And we know how many samples you need for this. Basically, square root of n times poly 1 over epsilon are necessary and sufficient. So what can we do in the k-modal case, the case we care about? Well, for the learning problem, our main result is that we have an algorithm which can learn a k-modal distribution to accuracy epsilon in this variation distance metric. And the number of samples it uses looks a little bit funny. It's k log n over epsilon cubed plus basically k cubed over epsilon cubed samples. And the running time is polynomial in all the relevant parameters, k log n 1 over epsilon. So you look at this, sample complexity, and you might say, well, that's kind of strange looking. It looks, you probably could guess, why do we have these two terms? It's sort of a two-phase algorithm. One of the terms comes from one phase, one of the terms comes from the other phase. And at first, it might seem like it's probably the wrong sample complexity. And in some sense, the second term probably is wrong, right? It's probably not what God's algorithm would do for this question. But the first term is actually right. So it's pretty easy to show a k log n over k over epsilon cubed sample lower bound for any algorithm for this problem. So yeah, Gabor?
Will you need the epsilon cubed then?
Swear to God. Cross my heart, yeah.
Which goes?
Whichever God you please, yeah. Yeah, I'll sketch, maybe later in the talk when we're closer to this, if you want, I can sketch the lower bound for the epsilon cubed. Yeah, so if we think of k as being significantly smaller than n, I guess if k is less than cube root log n or something, then our sample complexity is optimal up to constant factors. And as long as k is not too large, we're not doing too badly in terms of the number of samples. The main testing result is we have an algorithm that solves the testing problem. It uses, on the order of up to some log factor, it uses square root log n times k times poly 1 over epsilon samples. And it has also another phase, which is about k squared poly 1 over epsilon samples. It's also computationally efficient. And here the lower bounds aren't quite as tight, but we're in the right ballpark up to these polynomial factors. So we know that any tester for this problem has to use square root log n samples and has to use at least square root k samples. So the takeaway maybe from these two slides is that the testing problem for these distributions is provably easier than learning. We know that to learn, basically you need k log n over epsilon cubed. We can do it with about k log n over epsilon cubed. But for testing, we can beat that. It's more like square root log n. OK, so what's known about these kind of problems? Did anybody look at them before? There was some prior work. I guess for the cases of k equals 0 and 1, if we think of k equals 0, that's like a monotone distribution with no peaks or valleys. K equals 1 is like a unimodal distribution. So in those cases, in the testing literature, I think this was Batu, Kumar, and Rubenfeld, gave an algorithm which used log n cubed over epsilon cubed samples for this testing problem. They actually considered a slightly different problem where you have both p and q as unknown black box distributions, and you have to test equality between those guys. In fact, there was earlier work on the learning problem in the probability literature from the 80s. An optimal upper bound of log n over epsilon cubed samples was given for just the monotone or the unimodal case for the learning problem, and there's a matching lower bound for this as well. If you want, I'll sketch the lower bound for this in a bit. But as far as I know, nobody really looked at the case of general K prior to us. OK, so those are the basic results. If there are any questions, that's a reasonable point. If not, what's going to happen in the rest of the talk is I'll describe some tools that go into establishing these results. I'll sketch how we can get learning and testing results for k equals 0. K equals 0, the learning result, again, was due to Berger, but it's like really sort of cute and slick, so I want to mention it. I'll talk about our learning algorithm for general K, and if there's time at the end, I'll talk about our testing algorithm for general K. OK? OK. So some tools. We're really just going to need two tools, which I'll spend just a minute or two on each one. So the first tool is this nice Dvoretsky-Kiefer-Wolfowitz inequality, this DKW inequality for learning a CDF, any cumulative distribution function. Just a little bit of trivia. This Wolfowitz is the dad of Paul Wolfowitz, the political guy. The dad was a statistician, I think, or a probability guy at Cornell. I don't know anything about what the children of Dvoretsky or Kiefer have done at any point. OK, yeah, so what does this DKW inequality say? Basically, it says that 1 over epsilon squared samples is enough samples to pointwise learn any random variable, real-valued random variable CDF up to pointwise accuracy epsilon. OK? So just kind of saying it in math over here, if you take that number of samples, you have the kind of obvious empirical estimate of the CDF of your probability distribution or your random variable. So like say these are your sample points, these little dots down here. Then the obvious empirical CDF is like this green thing, right? No mass here. We got 1 point here, so my CDF jumps up to 1/5 since I have 5 dots, so on and so forth. OK, the DKW inequality bounds the maximum difference between the empirical CDF and the true CDF. OK? You can prove this using like VC theory. If you want like a very elementary argument, you can just use a Chernoff bound and really just a couple of lines of reasoning to get you just a slightly weaker bound with an extra log 1 over epsilon factor. Yeah. Anyway, the way I want you to think about this result, this tool, is that morally what it lets us do is it means if we have a distribution over n, or really any distribution over the line, we can partition it into pieces, into intervals, where each interval has about the same weight. Each interval has mass about epsilon. And we can do that using 1 over epsilon squared samples. Now, we can't actually do that, right? In general, if you have a distribution over the line, maybe it has mass 1/3 on some point or something. So of course, you can't make an interval which has weight epsilon there. But that's never a problem, right? If you have a distribution and it has a lot of mass on one point, you should be so lucky as to have this problem, right? You're going to get that point often in your samples. You can identify it. You can deal with it. It's never a problem. So think of this tool as telling us that you can do this. You can sort of chop up your distribution very efficiently into roughly equal sized buckets, buckets of mass epsilon each. OK? OK. Second tool, which is going to be handy, is that we can learn the PDF of a general distribution without too many samples. This is just restating the standard bound that we saw earlier about if you have an arbitrary distribution over n, and you want to learn it to variation distance epsilon, you can do that with n over epsilon squared samples. So just saying it in a slightly different way, if you have a distribution over n, you have your empirical estimator that you got from drawing m samples, then the expected variation distance of this empirical estimate is upper bounded by square root n over m. Okay? And this, too, you can prove with VC theory. You can also give a very sort of simple slick proof. This is from Berger's paper, where you just analyze the expected error on a given point. It's just a binomially distributed random variable. And then you can just bound the total error very simply using a concavity argument. So the bottom line of this, and this is something we'll use, is that you can learn any distribution over an n-element set to variation distance epsilon using n over epsilon squared samples. OK? So we'll use that. OK, so now I want to turn to learning and testing for k equals 0. So first we'll start with the learning problem. K equals 0 means, again, it's a zero-modal distribution. So we just have some probability distribution over the points 0 through n. And the PDF is like monotone increasing, say. And we want to learn it using few samples in an efficient algorithm. And this, again, I want to say is prior work. Berger did this back in the 80s. Okay, so what did Berger do? He proved the following thing. There's an efficient algorithm that learns any monotone, let's say monotone decreasing distribution over the endpoints to accuracy epsilon. The algorithm uses log n over epsilon cubed samples, and it's very efficient. It's a linear time algorithm. Okay. He also gave a lower bound of essentially log n over epsilon cubed for learning. He showed that it can take you this many samples to learn a monotone distribution. And Gabor, you seemed like you wanted to potentially see how something. I'll give. I can give you like a 30 second illustration of it. You have different buckets. So wait, I'm doing monotone increasing or monotone decreasing? Monotone decreasing. So we'll have a distribution like this. It's going to be monotone decreasing. So every bucket is going to be, the buckets are decreasing in height. You can see that. They're increasing in width sort of exponentially as we go along. So each bucket has the same mass. Okay? It's set up in such a way that each bucket has the same mass, and I guess there's log n over epsilon of these buckets. And within each bucket, I promise you the distribution is one of two forms. It either looks like this guy, that you have the top part and then you have the bottom part scaled like this, or else it's slightly different, or else the top part is a little bit higher and the bottom part is a little bit lower. Okay, so the possibility for the first bucket is it's either the white histogram or the red histogram. Similarly, for the second bucket, it's either the white histogram or the red histogram. And you set things up in such a way that it's guaranteed to be monotone decreasing, no matter whether it's white or red in each case. Okay, there's going to be something like an epsilon or 10 epsilon variation distance between white and red for each bucket. Okay, so basically, if you want to learn this distribution to epsilon accuracy, you've got log n over epsilon of these buckets. And for each bucket, what you're really trying to do is you're trying to tell whether a coin is like a 1/2 plus epsilon biased coin or a 1/2 minus epsilon biased coin. And so you need 1 over epsilon squared samples to fall in the bucket to be able to have a decent chance of making that determination.
Epsilon mass inside every bucket for the difference between the histogram, because the total mass, average mass of every bucket is epsilon over log n.
Yeah, the average mass of every bucket is epsilon over log n. If you rescale so that the mass of this is 1, think of just the conditional distribution over the bucket, then the variation distance between the red and the white histograms is epsilon or 10 epsilon. Yeah, but that's the idea. It's like you need to solve log n over epsilon learning problems, each to accuracy epsilon, and they're learning problems of just distinguishing a 1/2 plus epsilon versus 1/2 minus epsilon biased coin. So to solve each one, you need 1 over epsilon squared samples. So that's where the lower bound comes from. Well, if I get a sample that's in this bucket, it doesn't tell me anything about what's going on in the other buckets.
The log n over epsilon different possible distribution.
Yeah. If you want to think, the space of distributions, you have a binary choice for whether it's red or white here, and so on. Okay.
And basically, you just need to get half of them right.
Yeah. If you don't get half of them,
or 3/4 of them right.
Yeah, if you don't get this many samples and at least half of them, then you have at least half of them where you're not going to be doing well, and you're going to, Yeah, so it is log n over epsilon cubed. I know, it was surprising. We sort of worked this out without knowing about this prior work, and we were like, this must be wrong, but this is the answer. Okay, so that's a sketch of the lower bound. Let's see the upper bound. How does the upper bound work? It's actually via a kind of dual thing. The way I think of it, the key ingredient is this oblivious decomposition of the distribution. So we have a monotone decreasing distribution. We're going to think of decomposing the interval into log n over epsilon intervals. And these intervals have increasing widths. Okay, so the first interval is very narrow, then it gets wider, wider, wider. The last interval is quite wide. Okay? And we imagine this decomposition that has nothing to do with the actual structure of the distribution. It's like oblivious to what the distribution is, so we call these the oblivious buckets. Okay? So the main thing we're going to think about is essentially flattening the distribution. Right? The actual distribution within each bucket is something. Here is this little black segment. Here it's this black segment. But we're just going to imagine flattening the distribution, making it uniform over the bucket. Okay? So if your original distribution is this black line, P, the flattened version is just going to be constant over each bucket, but the amount of mass within each bucket is the same in the black distribution and the red distribution. right? The red line is just like the average height of the black line within the bucket. Okay? So Berger has this simple lemma. It's very cute. It's a couple lines to prove it, which says that for any monotone decreasing distribution with this structure of oblivious buckets whose sizes increase exponentially as powers of 1 plus epsilon, the variation distance between the original monotone distribution, the black guy, I should have made this red, and the red guy, the flattened distribution, is at most epsilon. Okay? You can, if you want to phase out for the rest of the talk, you can prove this on your own. It's not hard. It's a couple of lines with a telescoping sum. So given that, you can fit the entire algorithm and analysis of Berger for getting the log n over epsilon cubed samples into one slide. How does he do it? Well, he reduces the question of learning monotone distributions over this n element set to learning arbitrary distributions over the buckets. Okay? So let's think about it for a sec. The algorithm is just you draw L over epsilon squared samples. Remember, this is the number of samples you need to learn an arbitrary distribution over an L element set. Okay? So you get that many samples, which is log n over epsilon cubed samples from the monotone distribution. And then you say, well, I'm just going to try to learn the flat distributions over the buckets to epsilon accuracy, right? So what's your actual output hypothesis? I guess you take the empirical distribution you got, some number of points land in each bucket, you flatten it, so you have a flat distribution for the first bucket, flat distribution for the second bucket, so on and so forth, and that's your output hypothesis. Okay? And it's epsilon accurate. It's epsilon accurate because of the triangle inequality, right? We know that the true flattened distribution, the true distribution P and the true flattened distribution P bar, those are epsilon far from each other. And then the true flattened distribution versus the sort of empirical flattened distribution, well, that's just learning, two distributions over an L element set. So those guys are epsilon far from each other. And so that's it. Okay?
Is the flattened distribution still monotone?
No, it doesn't have to be monotone. Yeah, good question. Yes, sorry, I stand corrected. There's a subtle distinction here. There's an issue of like the way you should think of the distribution you're learning here is that it's really a distribution over L points. That distribution doesn't have to be monotone. The flattened distribution, the true flattened distribution does have to be monotone, you're right. But like the total, imagine that the black line were actually itself uniform, or we're like very, very slowly decreasing. Then the mass in the last bucket would be 1 plus epsilon times as large as the mass in the previous bucket, and so on and so forth. So the distribution over L points doesn't have to be monotone. It can sort of violate monotonicity by up to a 1 plus epsilon factor. Scaled by the width, yeah. So there's the question of scaling by the width, but scaling by the width doesn't affect the error rates as you do this, right? So basically you're not learning a monotone distribution in the final analysis. You're learning an arbitrary distribution over these L buckets. Okay. So that's it for the learning. Log n over epsilon cubed. I guess we've seen the upper bound and the lower bound. For the testing problem, Berger didn't, I guess there wasn't this notion of property testing. You can always use a learning algorithm to do testing, right? Because you could just learn your distribution to error epsilon over 100 or something, and then you have a very good hypothesis, you have the target, and you can compare them and see what you want. So you can easily get a log n over epsilon cubed sample algorithm for the testing problem just by taking Berger's result as a black box. But a slightly smarter thing to do is instead use his technique instead of just using the result. Right? So his technique is to basically have this reduction where you go from sort of the monotone problem over a domain of size n to the arbitrary problem over a domain of much smaller size, log n over epsilon. And you should just do the same thing for the testing problem, right? You have a known monotone distribution over n. So just think of the oblivious bucket decomposition. And now you have like this flattened distribution, which we can think of as like a known distribution over the much smaller set. You have an unknown distribution P, but it's promised to be monotone over the endpoints. Again, you have the bucket decomposition. The flattened guy is an unknown distribution, not promised to be monotone, but it's over a much smaller domain, right? So now you're just going to solve this testing problem. You have a known distribution, could be anything. Unknown distribution could be anything, but they're over small domains. And this is the problem that Lance and Renit and Toucan and all those guys solved back in the early 2000s, right? If you have an L element domain, they can solve it with essentially square root of L times poly 1 over epsilon samples. So that's the sample complexity bound you get for this monotone distribution testing problem. And there are similar lower bounds to the kind of thing I sketched over there. It's not hard to get a omega of square root log n lower bound for this monotone testing problem. Okay? So in a nutshell, that's the sort of getting us off the ground, the k equals 0 case. OK, so now I guess for the main topic of the talk, we'll talk about learning for general k. So we have a k-modal distribution with k peaks and valleys, and we want to be able to learn. OK, so again, the problem is we have some unknown k-modal distribution. It's got these k peaks and valleys, and we want to learn it from samples. What should we strive for? What are kind of the right bounds? Well, it's pretty easy that the right bound or the lower bound is k log n over k over epsilon cubed. This is, excuse me, almost an immediate lower bound, right? Because I'll just give you the promise that, hey, this k-modal distribution with the k peaks and valleys, it came from concatenating k constructions like this, right, where each one is over n over k points, right? So now you better solve most of those. So it's like I'm giving you a bunch of promises. I'm promising you that it's monotone decreasing up to n over k, then from n over k to 2n over k, I flip the picture, so it's monotone increasing, and so on and so forth. And you better solve essentially all of those problems to epsilon accuracy. So you're going to need k times, I guess, it's log n over k to be really honest about it, samples for this, because it's over n over k element domains. OK, so that's what we should aim for, right? We should try to come up with an algorithm that uses something like this many samples, k log n over epsilon cubed samples, and is efficient, right? We want it to run in poly time in k, poly log n, poly 1 over epsilon. So we don't even want to spend like n time to learn this thing. OK, and what do we know how to do? Well, we saw from the first part that we know how to efficiently learn monotone distributions. So in some sense, like there's a small amount of hidden information. If we had this small amount of hidden information, we'd be fine, right? If someone could tell us, hey, the peaks, they're like 17 n over 2, and so on and so forth, then you'd be done, right? So if we knew the peaks and valleys, that would be great. Of course, we're not going to have time to guess them. If you tried every possibility, there's n to the k possibilities. It's ridiculous. You might say, well, I could use something like the DKW inequality. It doesn't really matter exactly where they are, but as long as I get them kind of, I don't know, epsilon close with respect to where the probability distribution puts his mass, that should also be good enough. But even something like that, right? If you say, you want to just guess them up to some sort of like accuracy epsilon in terms of the PDF, that's also a lot of possibilities, some exponential in k, and we don't want to spend anything like that. OK? So what's the first approach you could do? OK, so maybe I should say I'm going to tell you about like a simple algorithm which solves the problem but doesn't get quite the right bound. And then we'll see a more sophisticated version of the algorithm that does get the right bound. OK? So first, the simple approach. What's a very naive and straightforward thing you could do? Well, you could imagine breaking up the interval into a lot of intervals, breaking up the whole interval, 1 through n, into a lot of intervals, say L intervals, where L is going to be a lot bigger than k. OK? So you just chop it up somehow. We have I1, I2, I3, so on and so forth. Well, the distribution is k-modal. There are only k peaks and valleys. So at most, k of these intervals can have a peak or a valley in it. Right? The other L minus k all have to be monotone. They're not going to have any peaks or valleys. So if we do something like this, right, and let's write p sub I sub j, or like p sub I for an interval I is like the conditional distribution over that interval. Right? If we think of breaking it up like this, we're breaking it up into many little learning problems, and most of these learning problems are ones we know how to solve. They're problems where it is a monotone distribution that you're trying to learn. So the most straightforward thing you can imagine trying to do is just run your monotone distribution learner on each interval. Most of the time it should work, and you get a pretty good answer, and you should be in good shape. OK, so how does this actually play out? Let's see it in a little bit more detail. I guess this is the algorithm. As the first step, we're going to use this DKW inequality. Remember, DKW tells us we can kind of chop up our whole domain into like little chunks of mass epsilon or so each. So let's actually chop it up into little chunks of mass about epsilon over 100k each. Okay? So each one of these intervals has pretty small mass under p, something like epsilon over 100k. And we're also going to estimate the mass of each interval to reasonably good accuracy, 1 plus or minus epsilon, because eventually we're going to have to combine hypotheses over these distributions, and we have to know how much weight to give to each one. Okay? What are we going to do then? Well, we're just going to run the monotone distribution learner on each of these subintervals. Okay? Now, you might say, there's this annoying thing, like I have an interval, and I don't know whether it's monotone increasing on that interval or monotone decreasing on that interval. So it's not a big deal. You just run the monotone learner twice. You run it once, the sort of monotone increasing learner, run the monotone decreasing learner, and you can do some simple hypothesis testing to see whether one of these hypotheses is a lot better than the other hypothesis. Okay? So you do that. You run the monotone distribution learner on each interval. You pick a good one, right, the increasing or decreasing guy. And then you just put the hypotheses together in the obvious way. For each interval, you have your hypothesis. You scale it by the appropriate amount of weight. And this is just your combined hypothesis distribution.
That may not be k-modal, maybe itself certainly not k-modal, right? I mean, if
yeah, there's no guarantee that even our monotone distribution learner gives us a monotone distribution back. You can make a monotone distribution learner give you back a monotone distribution by doing something called, I think, the adjacent pools violator algorithm, where it's just the obvious thing. If it should go like this, and it goes like this, you average those two guys and repeat, and it never hurts you, but yeah. Rishi, yeah?
How do I ensure that the probability of each of those intervals is around epsilon over 100? You don't know that.
That's this DKW inequality, right? Remember this DKW inequality? Morally, it lets us, by using, so in the next slide I'll talk about the number of samples we need for this. But you're right, there could be heavy points. I mentioned this earlier. There could be very heavy points which have mass, more than epsilon over 100K. But if so, we're going to, every 100K over epsilon points, I'm going to hit such a heavy point, and I'll be able to recognize it as heavy. And you can just kind of deal with them in a brute force way. So. Yeah, so for the purposes, it's good to call attention to this. For the purposes of the discussion, just pretend every point has mass at most epsilon over 1,000K or something, and then you can do something like this. Yeah?
You always seem to position it obliviously. Does it make sense to maybe try to find the peaks and valleys by sampling?
Yeah, we're going to do something like that as the more sophisticated approach. You'll see that. So yeah, hold that thought for a little bit.
DKW is not oblivious, though, right?
DKW is not oblivious, no. Yeah, DKW is just, you
look at the samples.
You look at the samples, you write down your empirical PDF and then CDF, and then you just go with it. Yeah. Okay, so let's see actually how well does this work. So we're running DKW. We want to get intervals of width epsilon over 100K or so. We want to be able to sort of isolate little chunks of that much mass. And I guess we actually want to know the mass to an extra epsilon factor of accuracy so that our scaling factors are ultimately right. So this first phase is going to cost us something like k squared over epsilon to the 4th samples. But don't even worry about the first phase too much. The second phase is more of a concern. In the second phase, we have these 100K over epsilon intervals, and we're going to run our monotone distribution learner on each one of them. And if you remember, our monotone distribution learner costs us, sorry, this should be a capital N, costs us log n over epsilon cubed samples to run it. And we're running it k over epsilon times. So our learning phase over here is going to cost us k log n over epsilon to the 4th samples. Okay? And these two terms are the sample complexity of this algorithm. And just to convince you that it actually works, right? What's the error of our combined hypothesis going to be? Well, we could have totally screwed it up on up to k of the intervals. Or up to k of the intervals that actually had peaks and valleys, so it was non-monotone, and all bets are off as to how we do there. But those k intervals each have mass at most epsilon over 100K. Right? So that only costs us order of epsilon error. What else could go wrong? Well, maybe we didn't estimate very correctly, or we made some small errors in estimating the mass of each interval when we do the final scaling. But again, if we get them up to some epsilon accuracy, that's only going to cost us an epsilon. And finally, when we actually learn this conditional distribution, we don't get it exactly right. We make some epsilon error in that. So that's another epsilon, but this, this works. This gives us epsilon accuracy. Okay. So it works, but it's not that great, right? We saw the right lower bound is something like k log n over epsilon cubed, and we're paying k log n over epsilon to the 4th. Why did we pay that? We paid it because we ran the monotone distribution learner k over epsilon times, right? So if we want to save this epsilon factor and get something closer to the right bound, we don't want to run our learner so many times, okay? So what do we want to do? Well, it would be nice if we could check on the cheap, more cheaply than actually running the learner, whether a given interval is monotone or not before we run the learner, right? Then we wouldn't run the learner as many times and we'd get some savings. So this is, I feel I'm on camera, so okay. You often hear this motivation stated, like for property testing. Property testing can be like a useful diagnostic that you run before running a more expensive learning algorithm. I'm not sure I know of that many actual occasions where that kind of thing happens, but this actually does seem to be such an occasion where maybe we could do it, right? We ran a learning algorithm more times than we felt like we should have run it, and if we could do some kind of cheaper property testing, that would save us something, and we wouldn't have to run it so many times. Okay? So that's the sort of new ingredient for the smarter, the real learning algorithm. Actually, there's two ingredients of the real learning algorithm, and I'll tell you about them now.
The testing algorithm is good on the log n factor, but not good on epsilon factors.
I didn't tell you what my testing algorithm is yet. You'll see the testing algorithm we actually use is different from the tester that we talked about.
Okay.
Yeah. Okay. Yeah. So this is the testing algorithm we're going to use. What is the testing problem that really we'd like to solve for this purpose, right? We have samples from a k-modal distribution. We have a promise that it's a k-modal distribution we have samples from, but we don't know what that k-modal distribution is because it's the one we're trying to learn. What do we want to do? We want to answer the question, is this k-modal distribution actually monotone or not? If it is monotone, then we're going to be like, great. Right? And if it's not monotone, then we're going to say, OK, it's non-monotone. This is the kind of thing we want to know in order to do our learning more efficiently. Right? We don't want to run our learner on non-monotone chunks. So this is a testing problem we'd like to be able to solve. If we could do this, it feels like it should be useful for our learner. And notice, like this promise that the distribution is k-modal, it's got to be crucial, right? Because we saw this kind of lower bound. This problem, if I erase the words k-modal here, right, then we know that this testing problem is really hard. You need like omega of square root n. It should be capital N again. If we don't have the k-modal promise, you know you're going to need omega of square root of n many draws to tell is your unknown distribution monotone or far from monotone. Right? But maybe the promise that it's k-modal actually lets us do this without paying some horrific factor like that.
So actually, before we
Yeah.
So why is it that so I thought only k of the intervals are where you are non.
Yeah, there's k peaks or valleys in the distribution.
Right,
So
so
any.
you won't save so many queries if you just know beforehand that.
Imagine doing this on subintervals, right?
Yeah, you'll see. We're going to do this. We're going to run this tester repeatedly, and we will get a savings. Yeah.
Oh, okay.
Yeah.
But at least from the previous slide, it was not clear that.
Yeah, probably nothing was clear from the previous slides, but yeah, it shouldn't be totally. It probably isn't totally clear yet, but I'll show you the ultimate like real algorithm in detail and argue that we do get this savings in more detail. Okay. But just for now, we'd like to have an algorithm for this testing problem, and it's conceivable we could have an efficient algorithm for this testing problem because of the promise that the distribution is k-modal. Okay. So in fact, there is an efficient algorithm for this testing problem. I'll convince you of this in a couple slides, so not immediately, but I claim there's a k squared over epsilon squared sample algorithm for this testing problem, independent of n. Okay, so testing whether a k-modal distribution is monotone or far from monotone, we can do it with k squared over epsilon squared samples. It's actually a super simple algorithm too. Anyway, yeah, so let's just, for the moment, pretend we actually have this testing algorithm. We're going to use it at a high level. I'll tell you more detail in a second, but at a high level, we're going to use it to identify subintervals of our big domain where the distribution is monotone. But there's this suspicious-looking space here, and there's a suspicious-looking space because, of course, it's a tester. It can't really tell us, cross my heart and hope to die, the interval is guaranteed to be exactly monotone. It can only tell us that the interval is close to monotone. So if we're going to run the learner on some supposedly monotone interval that we get from this, we better have a learner that actually works if the interval is it doesn't just work if it's truly monotone, it works if it's close to monotone. So in other words, we want something like an agnostic learner for monotone distributions, right? We're going to be in a situation, if we run this tester and we have close to monotone intervals, we're going to be in a situation where we have an unknown distribution. Think of this p as like the conditional distribution over some interval that passed our test. So we have an unknown distribution that is close to monotone. Say it's opt close to monotone. Well, we want to learn it to high accuracy something like opt plus epsilon. Okay? This is the kind of situation we're going to be in. So I haven't seen this phrase, but it seems like the right phrase to me, like you're trying to kind of agnostically learn a monotone distribution. Notice this is just the exact original distribution learning problem, learn a monotone distribution in the case opt is 0. If the distribution really is monotone, you're supposed to get an epsilon accurate hypothesis. And if it's not monotone, if it misses by some amount, you're allowed to have a hypothesis whose error grows like that.
So anyway, when we call this algorithm, opt is going to be
Yeah, yeah.
But so then just the usual monotone, I mean the usual monotone distribution learner would do it.
You've totally anticipated my next slide, yeah. Yeah, except with one tiny wrinkle. So you're completely right. There is an efficient algorithm for this problem. It uses log n over epsilon cubed samples. And just like Swastik said, the original monotone distribution learner that we saw, where we just have these oblivious buckets and we carve things up, it does the job. If you do the analysis of that earlier algorithm, in this case where you actually, are not perfectly monotone, but you're opt far from monotone, at least the way we did the analysis, it seems like you end up with a hypothesis that's 2 opt plus epsilon, because you use the triangle inequality, and so your final hypothesis ends up being 2 times opt plus epsilon, but that's not going to be a problem, right? We're going to end up running it exactly like you said, with where we're epsilon far from monotone, and so okay, epsilon plus epsilon versus 2 epsilon plus epsilon, it doesn't matter for us. Okay? So these are kind of the 2 ingredients, I would say, that are in the real algorithm that weren't in this first algorithm. There's this property tester, and there's this observation that, hey, we actually have to be kind of agnostically or semi-agnostically, because of this factor of 2, able to learn monotone distributions. OK, so now let's see the actual learning algorithm. All right? There's going to be 2 phases, in keeping with the sort of 2 terms in the sample complexity bound that we saw earlier. The first phase, again, is going to be to use the DKW inequality to divide the whole interval, 1 through n, up into these subintervals, where the subintervals are going to have the property that they're each pretty small. They each have mass about epsilon over 100k. Okay? So that's our first thing that we do. We have these subintervals I1, I2, I3, I4, so on and so forth. Now the second step, this is how we're going to use the property tester. We run the tester. Notice I say testers, not just one tester, because again, there's this annoying thing, like is it monotone increasing or monotone decreasing? You have to run them both, right, and see if either one of them says yes. So we're going to run the increasing tester and the decreasing tester on I1. Hopefully one of them is going to say, yeah, it's increasing on this interval. Let's say that one of them says, it's increasing on this interval. If so, then we run the tester again on the union of I1 and I2, this conditional distribution. Right? Is it increasing on this interval? Say it says yes. Then we run it on I1, I2, I3. This whole thing, is it increasing on this interval? Well, it looks like it's pretty close to increasing on this interval, so probably our tester will again say yes. Then we run it on I1, I2, I3, I4. We say, is this distribution, conditioned on being in here, increasing? Presumably it's going to say no, right? It says no, and so what do we know? We know that I4 was kind of a spoiler interval, right? When we didn't have him in it, it was close to increasing, and when we added him in, it wasn't close to increasing anymore. So we're like, this interval is a pain, we're going to mark it and deal with it later, or actually not deal with it later. But anyway, we mark it, and so now we continue, we just keep on going from the right. We're going to look at I5 and say, is this interval increasing? It is, or decreasing? We run them both again as usual. Is this interval, say, decreasing? No. Is it increasing? Yes. OK. Run it on I5 and I6. Is this interval increasing? Yes. OK. Run on I5, I6, and I7. We get a no. Whenever we get a no, we mark the interval that causes us to get a no, and we continue. OK? OK, so the way we're going to think about this is like, what happens when you mark an interval? Well, when you mark an interval, like you mark I4, since you didn't mark the previous guy, that sort of super interval, the union of these guys is close to monotone. So that's like a good chunk on which to run your learning algorithm later. And also, maybe more important, if we mark an interval, if both our testers said no, over this whole stretch, you're not close to monotone increasing and you're not close to monotone decreasing, there must be at least one peak or valley somewhere in that block. It's not necessarily guaranteed that it's like in this last guy, actually. Like here, the peak was actually here in I3. But if there were no peaks and valleys in this whole block, then the whole thing would be monotone increasing or monotone decreasing, and you wouldn't have said no. OK? So we do know that every time you mark an interval, you use up at least one peak or valley. So there's going to be at most k marked intervals in total. OK? So that's what we do. That was the first phase of the learning algorithm. And what have we got after this first phase? We have that the original domain is broken into these sort of 2 different flavored chunks. The first types of objects it's broken into are these super intervals, S1 through Sk. And each of these super intervals is close to monotone. So we could run like our semi-agnostic monotone learner on that. And then we have these marked intervals, right? We know that we have at most k of them, and we know that each one doesn't weigh too much. So we're just going to ignore them. We're not even going to try to learn on them. And we can get away with it. It costs us an epsilon factor. OK? So the rest of the algorithm is exactly what you'd think. We run this sort of semi-agnostic monotone distribution learner on each super interval. We get a good hypothesis on each super interval. and then we just combine all the final hypotheses over the superintervals with the empirical weights. So again, we don't even try to get it right on the marked intervals. Okay. So that's it. It doesn't cost us too much. Let's just verify that it costs what I claimed it costs. The number of samples we need, well, what did we do? We had these 100 k over epsilon initial intervals, and we ran the tester, which used, I think, k squared over epsilon squared samples for each of those guys. So this is where the k cubed over epsilon cubed term comes from. And actually, if you notice, there's a little twiddle here. The twiddle here is because I'm running my tester like k over epsilon times. So I kind of want it to give me the right answer with probability, failure probability, something like epsilon over 10k. I can't just say 2/3. 2/3 is good enough. So that was like the first phase. That's this k cubed over epsilon cubed term that we get in the sample complexity. And the second phase is we actually ran the learner just k times now instead of k over epsilon. And each run of it costs us log n over epsilon cubed for the samples. And if you check, did it actually work, you can just tick through the possible sources of error. Well, we paid full price on these k marked intervals. That was epsilon over k for each one, but there's just k of them. We estimated, we only approximately learned, of course, each distribution over a superinterval. So that's, again, like an epsilon error that we pay. And our scaling factors, right? We don't know the exact weight of each superinterval, but we know it approximately. We know it in particular to an additive epsilon over k, and there's k superintervals. So the error we incur from that is at most epsilon. Right?
So do you know anything about the lower bounds for this testing problem that you use?
Do I know anything about lower bounds for the testing problem? Yeah, the next couple slides are about the testing problem, so let me hold that question for a second. I don't think I have no, we don't know lower bounds better than root k. And our upper bound is k squared over epsilon squared. So, and the root k is trivial lower bound for the testing problem, just this usual thing. So yeah, so it's possible you can improve there. Okay, so this is the algorithm and its analysis, but I didn't sort of fully convince you yet, maybe because I still owe you, this tester, right? This was this problem where we have an unknown distribution. It's promised to be k-modal. And we want to tell, hey, is it actually monotone or is it epsilon far from monotone? And I claim that we have a k squared over epsilon squared sample tester for this problem. So the next couple slides, I'll try to convince you of that. It's really a very simple algorithm, and the analysis is also very simple. The main idea behind it is the following not so deep insight. It's that if you have a monotone, say, increasing distribution like this, the black line that I drew, and you have two intervals, say I1 and I2, where I1 is to the left of I2, then the average height, say, of the distribution over the left interval is going to be less than or no greater than the average height of the right interval. Okay? It's hard to argue with that, but it's basically all you need for the tester. So here's the tester. You should basically ignore the first line. The first line says the usual thing, run dkw, so you get like a decent estimate of the PDF of the whole distribution. And you might say, wait, how can you have a good estimate of the PDF of this whole distribution? You're drawing k squared over epsilon squared points, and the distribution is over n points, so you don't really have a good estimate. But all we're going to need is that this empirical PDF is good in the sense that it doesn't make too much additive error on any interval. And that's exactly what DKW gives you. DKW gives you a bound on the CDF error. If I have a bound on the CDF error over here and a bound on the CDF error over here, 2 times that bound gives me, a bound on the error of the PDF over this interval. Okay? Okay, so we have a pretty good PDF, an estimate of the PDF over any interval. And then the tester is, you just see, are there any 3 points, A, B, and C on the line in order, such that the average height of the empirical distribution over AB is significantly more, this kind of funny quantity, noticeably more than the average height of the PDF over the right interval, right? So here we have this is the average height from A to B. It should look like this. If it's a monotone increasing distribution, your average height here, which is just the mass divided by the width, this should be less than this, the average height here. We just saw that, right? But if it ever goes the other way, if there are any 3 points where it goes the wrong way by sort of a slightly noticeable amount, so it's higher here and lower down here, then you should say no. And if it's not like that, if every 3 points sort of respect the way it should go, then you should say yes. Okay? So we can just sketch the analysis. If the distribution is truly monotone. If we had the exact right PDF, right, if we didn't have p hat, but we had the actual p, of course, this would always be less than, the left-hand side would always be less than or equal to 0. So certainly we'd never fail. And because we have DKW, we have good estimates of the PDF, we're not going to fail in this case either. Okay? So what about the other direction? The other direction, soundness, is a little more interesting. I guess it relies on this lemma. The lemma essentially says that we have to get k-modality in there somewhere, right? The lemma says that if you are a k-modal distribution, and every 3 points, don't satisfy this inequality, satisfy the opposite inequality, that the difference in the average heights between the two contiguous intervals is upper bounded like this, then in fact your k-modal distribution is going to be epsilon close to monotone increasing. Okay? So if you see a statement like this, like how would you argue a statement like this? Well, there's only one way you could try to argue, there's only one way we thought to argue a statement like this, which is you're starting with your k-modal distribution. You have this guarantee for any 3 points you want. So we're just going to apply this guarantee sort of, whenever we need to apply this guarantee and maybe fix the distribution. We're going to mend the peaks and valleys of the distribution. And we're going to do that k times because it's k-modal. Every time we do it, we'll spend something like epsilon over k in variation distance. And so we'll go from our k-modal distribution to an epsilon nearby increasing distribution. Okay? So these next few slides are a titanic struggle for me because I'm not too good with visual things. So I want to really savor them. So OK, this is the lemma that kind of tells us, or this is the process by means of which we prove this lemma. We can correct kind of a peak of the distribution. So say your distribution goes up and then goes down, something like this. The idea of how we correct the peak is we're going to draw a line. We're going to drop a line. And we're going to let the line stop once sort of the mass it cuts off on the peak equals the mass that's missing in the valley. So that's sort of like the variation distance of this local violation of monotonicity. So yeah, savor it. Thank you. Thank you. Thank you. OK, so we're in a situation like this. And then what are you going to do? You're going to do the obvious thing. We're going to correct the peak by just bulldozing the mountaintop down into the valley. So I hope this works. Yeah. Yeah, so we just flatten it out. Where's the applause? Thanks. Thanks, guys. Yeah. So that's just this local process of correcting it. And really just, this is, maybe this is a pain to look at, but this is the entire proof that the process works, right? I don't know how much detail of this we want to go through, but we can go through at least maybe the first line or something. So this mass, the mass of the peak, is equal to what? The total probability mass of the distribution between A and B, that's like the total mass under the hill, including this stuff down at the bottom, minus the mass of the rectangle. I didn't draw the rectangle, but its upper boundary is this line h, and its height is h, its width is A minus B. So the mass of this peak is this probability minus the height times the width of the rectangle. We know, because we dropped the line exactly to that point, that equals the mass of the valley. The mass of the valley is h. Again, the height of the rectangle, the height of the line, minus the height of this rectangle now that's bounded by this. So it's h times c minus b is the mass of the rectangle, and then we have to subtract off the mass of the distribution. That gives us the height of the valley. So then just some completely trivial algebra, rearranging this, we get something like this. Rearranging this, we get something like this. And if we add these two equations, we have PAB over b minus a plus 1 minus h. We're going to add that to h minus this. And we get exactly what we want, right? The average height from A to B minus the average height from B plus 1 to C equals this thing. And by assumption, we know that this thing is small. So we get that the height of the peak, the height of the valley are small. So in other words, we incurred epsilon over 2k variation distance with the bulldozer. And we can do this k times, and we don't mess it up. By the way, the last time I gave a talk on this, I should have changed the slides. Someone used the phrase, I think it was Meyerson leveling for this. Someone in the audience was like, oh, this is like Meyerson leveling. Does anybody? Well, the internet will tell us then if this goes up on the IS website. But yeah, I'm sure obviously something like this must have been done many times. It's very straightforward. OK, so that's it. So that's the tester. I don't want to run over, so I'm going to, I think, skip everything I was going to say about testing for general K. Just to remind you of the problem. It was that we have a known k-modal distribution. We have an unknown k-modal distribution. We want to know if the unknown distribution is the same as this versus far from it. And in a nutshell, just in one slide, the way we do it is we use actually our simpler learning algorithm. The first learning algorithm I showed you can be used as the tester, can be used as an ingredient in the tester. Why is that? Well, the simpler learning algorithm broke the interval up into a bunch of these small intervals, right? These little pieces. Most of those little pieces really are monotone. So I can run my monotone tester on most of those little pieces. I actually have to manipulate it a little bit because I have to take into account the peaks and valleys of the known distribution Q. But in a nutshell, you break up the whole interval into a bunch of pieces. You run the monotonicity tester on each piece. Is this little chunk of P equal to the corresponding chunk of Q? Is this little chunk of P equal to the corresponding chunk of Q? And you accept only if almost always the little chunks do seem to be equal and the mass of the little chunk seems to be the correct mass. So some easy analysis gives you that this works.
And so the basic thing you're using here is because of Q, you know where all these things should be monotone and what direction they should be monotone.
Yeah. So you can do So this K, like you take your initial decomposition into intervals, and you're like, well, Q actually has peaks here, here, and here, so I should slice up this interval into two pieces because that's where the peak of Q is, and so on and so forth. Yeah, it's messy and not that interesting, so let's skip it. So it works. You could imagine using the smarter learning algorithm, but at least some subtleties arise. So far we haven't used the smarter learning algorithm yet. Doesn't seem like you'd save very much, and it would be a little more complicated. So we're almost done. Just to wrap up, we looked at algorithms for these learning and testing problems for k-modal distributions. We have algorithms that are pretty efficient in terms of their running time and their samples. The upper bounds are pretty close to the lower bounds. And the takeaway message is that the testing problems are provably easier than the learning problems, and also that there seem to be nice connections between testing and learning for these problems, right? Our learning algorithm had this testing component, and I kind of glossed over it at the end, but our testing algorithm is based on the same things we did for learning. In terms of future work, these are the least inspired directions for future work you could possibly imagine. That's to attack the problem in more generality and in more specificity. So in terms of more generality, our sample bounds are basically like k log n if you pretend epsilon is a constant. That's obviously very small compared with the really general problem of learn an arbitrary distribution where the bound is n. So I don't know, it seems plausible that there are interesting families of distributions where you have some intermediate sample complexity bounds that you could think about trying to learn. And so that's more general. In terms of more specific, it seems plausible to me that there actually are restricted subclasses of k-modal distributions where you could do even better than we've done. In particular, one special case we analyzed in some different work is a very special type of unimodal distribution. Imagine you have n coins with different unknown biases, okay? And you toss all n coins and you see how many heads you get. So you have a sum of n unknown Bernoulli random variables. Okay, not a binomial distribution, you don't know the different PIs for these guys. And you want to learn a distribution like this to epsilon accuracy and variation distance. Well, it's going to be unimodal. It's definitely unimodal. So you could just hit it with what we're doing, or hit it with the Berger's stuff for unimodal distributions and learn it with log n over epsilon cubed samples. But it turns out that if you look at this distribution more closely, you can actually learn it from poly 1 over epsilon samples independent of n. So I think there are some cases where more structured classes of, say, k-modal or unimodal or whatever distributions you can learn even more efficiently. And there might be some interesting things to do there. So OK, now I really ran over and I'll stop. Thanks.